Chapter 4.2 Part 2. Chapter 4.2 is about solid material properties, and in this second part we will see stress, strain and the Young modulus. In 4.2 part 1 we learned about Hooke's law, and this is the second video which is for part 2. By the end of this section you should be able to calculate tensile or compressive stress. For example, if you stretch a wire, then you are exerting a tensile force. Okay, but if you compress something, then that is a compressive force. So you get compressive stress. If you pull a wire, okay, let's consider something like a spring, then it's easier. Now there are springs that can be compressed and also that can be extended. You can pull the spring. For example, if you see the shock absorber system in a car, it consists of springs. Those springs can be pulled as well as compressed. So if you apply a pulling force on those giant springs, then you are exerting a tensile force because you are pulling it. Same thing if you consider a wire. If you pull a wire, that is a tensile force. Okay, there is a tension in the wire as a result. Then the other one is the compressive force. So again, if you push the spring on either end towards each other, then you are compressing the spring. That is, you are applying a compressive force, so you get a compressive stress. Now this equation is the equation for Young modulus. Sorry, not this one. I think it's here. So we have this. Yes, this is the equation. Young modulus is equal to stress over strain. So this stress can be a compressive stress or a tensile stress. We will see the details. So you have to know this. Young modulus is equal to stress over strain. Now this Young modulus is constant for a certain material. Previously we saw spring constant. That spring constant, even though the spring is made of the same material, depending on the shape or the size of the spring, the value of K changes, but the value of Young modulus is the same. So that's why we are using Young modulus, because it is a constant for a certain material, whereas the elastic constant or spring constant that we saw earlier in F equals Kx, that K can be different even for the same material. For example, if you see a big spring and a small spring are made of the same material, the values of K are different, but the value of the Young modulus is the same. Okay, then calculate tensile or compressive strain. Again, if you pull a spring, then you have a extension. Okay, now what is strain? Strain is extension over original length. Now this can be also how much it is compressed by. So it can be extension or the amount that the spring is compressed by, extension or compression. So then if you extend it, if you pull it, then you have a tensile strain. If you compress the spring, then you have compressive strain. So this is the equation you see here. This is the equation for strain. Then what about stress? The equation for stress is this: force over cross-sectional area. Now this is the same unit as pressure, because newtons per square meter. But in the equation for pressure is force over area. Now here the difference is this is cross-sectional area. Okay, so if you consider a wire, if you see the cross-section of the wire, that is what you have here. But in the equation for pressure, it's just force over area on which that force is applied. In the case of pressure equals force over area. Force divided by area on which the pressure is applied. Now here the word we use is stress. This is different, but the unit is the same. Okay, then Young modulus. You can see Young modulus is equal to stress over strain. That is this quantity divided by that quantity there. Okay, first we will see something about these quantities. So here you have stress, that is force divided by cross-sectional area. Now this force can be a compressive force or a tensile force. See, tensile or compressive stress depending on whether the force is tensile or compressive. And we can assume in these calculations, we assume that the cross-sectional area remains the same. Okay, the example of different, but they are measured under comparable conditions. And to help you understand this better, there is an example. A cylindrical column, stone column, has a diameter of 60 centimeters. It's labeled and supports a weight of 2500 newtons. What is the compressive stress in the column? So compressive stress, because you see the force is trying to compress this. Okay, it's trying to decrease the length, in other words. Okay, if it's a compressive stress, it will try to decrease the length. If it's a tensile stress, it will try to increase the length. So first we can calculate the area of cross section, because stress is equal to the force divided by the area of cross section. Now area of cross section, since it's cylindrical, the area of cross section will be area of a circle, and the area of a circle is pi r squared. So pi into r is the radius, which is half of this. This is then 30 centimeters, but we have to convert it to meters so that we get the answer in SI units. Then you can see that is what we get in this. So now we can use the equation. Stress in unit is SI unit is pascals, is equal to force over cross sectional area. The force is 2500, okay, divided by the area. Okay, by the way, remember there is a compressive force this way and also this way. Okay, but we use only one of those forces. So even when you're stretching also, you have, when you apply the force from one side, there will be another force from the other side, but we just consider one of the forces. Okay, finally we get 8850 pascals. This temple support column is under a compressive stress of 8850 pascals. Now let's see how we can use this equation. Here the original length is constant. Over here the cross-sectional area is constant. Even when the force is applied, we assume that the cross-sectional area is constant. Similarly over here the original length is constant. And these are the symbols we use. Delta x is the extension, which is the difference between the final length and the original length. X is the original length. As strain is a ratio, it has no units. However, it is often expressed as a percentage by multiplying the ratio by 100%. So no unit, the units here and here cancel out, no unit. Copper wire of length 1.76 meters is stretched by a force to a length of 1.80 meters. Now to find the extension, you have to subtract this from this, and you can see the calculation here. So we use this equation. This is a Greek letter epsilon. This is the Greek letter sigma. You have capital and simple sigma. This is simple sigma, and this is simple epsilon. So now the original length is 1.76. Then you get this, which is that, and you can convert it to a percentage and write it like they mentioned here, and that will be 2.3%. So it has extended by 2.3% of the original length. So the copper wire has a tensile strain of 2.3%. Then Young modulus will be stress over strain, very easy. So that is sigma over epsilon if you look at the symbols, and here we have capital E, or you can also say this is capital epsilon. Epsilon again is a Greek letter. Then previously we learnt about the spring constant. It's also called the force constant. Okay, here we can also say stiffness constant. Now if you look at the next chapter, okay, the next part 3, here also you see the word stiffness constant, that is used for Young modulus. But if we look at this here, The stiffness constant K from Hooke's law relates to a particular object such as a spring. Okay, so that is what the previous part. So you see the same word is used for K and also for E, the Young modulus. For a material, the Young modulus E is the stiffness constant for the material in general, regardless of a sample size. See, I mentioned this in the beginning of the lesson. E is a constant for a certain material, but K, even if the object, say for example, is made of the spring, it will be different for different springs of the same material, the value of K, but the value of E is the same. Then I think we covered all this. Alright, so let's just go through this bit and also this paragraph. Some important points are here. Tensile or compressive stress is a measure of the force within a material sample. So it's within the material, but it takes account of the cross-sectional area across the sample. This allows the force comparisons to be made between samples of different sizes, so that they are measured under comparable conditions. Okay, that is regarding stress. Now let's look at this. Tensile or compressive strain is a measure of the extension or compression of a material sample, but it takes account of the original length of the sample. This allows extension comparisons to be made between samples of different sizes. So in this case, when we say size, it is the length. Here it is the cross-sectional area, so that they are measured under comparable conditions. And here about Young modulus, if a material is deformed elastically, it will be proportional to the strain. Okay, in the chapter 4.2 part 3, we saw the graphs of extension, stress versus strain. So there it is a straight line up to the limit of proportionality. So the gradient of that graph is the Young modulus. If a material is deformed elastically, it will be proportional to the strain with a constant of proportionality. It is measured, that is a measure of the stiffness of the material. Stiffness of the material. So that is what we call the Young modulus here. Now don't confuse that with the stiffness constant K. So that also we call stiffness constant. This also we call stiffness constant. Stiffness of the material, how much it deforms under a certain stress. The stiffness constant is called the Young modulus. Thus, the Young modulus is a measure of the stiffness of a material, which takes account of the shape and size of the sample. So that different samples of the same material will all have the same value for the Young modulus. The idea of stiffness is a measure of how much the material deforms when forces are applied to it. So very important, it's a matter of using these equations. So you have to remember this equation, and this one. And also you have to be able to substitute what is here for sigma F over A and this one, and then you will get this equation for Young modulus with the quantities for stress and strain. We will see that now. Okay, you see here this. So what you do is you substitute for sigma F over A, and for epsilon, that is the strain, symbol for strain, delta x over x over here into this equation, and then you will get this equation. The definition for Young modulus also includes the fact that the material must be undergoing elastic deformation. If you stretch something up to the elastic limit, as long as you don't stretch it beyond the elastic limit, the material is said to be elastic. So when the deforming force is removed, it returns to its original length or shape. But if you stretch a material beyond its elastic limit, the material is no longer elastic, it becomes plastic, which means when the deforming force is removed, it doesn't return to its original shape or length, it is permanently deformed. So remember, up to the elastic limit, when the deforming force is removed, it returns to its original shape. But beyond the elastic limit, if you stretch something beyond, if you apply a force so that it is going beyond the elastic limit, it is no longer elastic, it becomes plastic, which means when the deforming force is removed, it doesn't return to its original shape. So we say it has permanently deformed. It is plastic now. It's elastic if it returns to its original length when the deforming force is removed. If it's plastic, if it doesn't, that is when you stretch it beyond the elastic limit, if it's elastic material. The definition for Young modulus also includes the fact that beyond the limit of proportionality, this equation will no longer work to calculate the stiffness of the material. Now, limit of proportionality, from the name itself, that is limit of proportionality. Proportional means the graph should be a straight line passing through the origin. So it will be a straight line up to that point called the limit of proportionality. So we can use this equation, this one, for the graph of stress versus strain to calculate the Young modulus only to the straight line portion of the graph, because this means it's proportional. So that's why we use the straight line portion of the graph to calculate that. So from the original definitions of stress and strain, Young modulus can also be calculated from this. So I told you how to get this. You substitute this and this for that and that, stress and strain. Then simplify, you get this. Rearrange, you get this. So let's see how we can do another calculation. The copper wire from above has a diameter of 0.22 millimeters and was stretched using a force of 100 newtons. Here also we have copper, but let's see. What is the Young modulus of copper? So first, to find the Young modulus, we need the stress and the strain. And remember, stress is force over cross-sectional area. And here you can see the strain was calculated earlier. So it's referring to the same thing, because if it's the same material. So you can see this is 0.023. So we use that value for strain, this one. Okay, the symbol of strain is epsilon, the symbol of stress is sigma. All are Greek letters. Now the diameter is given, so we can find the cross-sectional area, which is equal to pi r squared, and our radius is half the diameter, so we divide this by 2, and since it's in millimeters, we convert it to meters. You can see the conversion is done here, and then you get the cross-sectional area in square meters to be this value. Now sigma is equal to F over A. The force is 100 newtons, the area of cross section is this. Then we get this sigma, that is the stress. Then we apply it in this equation to get the Young modulus. Now you see Young modulus has the same unit as stress or pressure, which is pascals, because the strain doesn't have a unit, its units cancel out, because strain is extension over original length. Note that the stress has been calculated from the original data and the rounded value has been used in this calculation to give the value shown here. Okay, so you can see even a diagram is drawn. 100 newtons, 1.76 meters, 0.04. See this one. Okay, now here you have additional 100 newtons. Okay, so that will be the Young modulus for copper. Alright, so we have arrived at the end of this this chapter, and in this book you get the key definitions normally at the end of each subchapter. It's very important that you study this, because in the exam papers you may have to use these equations or you may have to write these definitions, so make sure you memorize them with understanding. The Young modulus is the stiffness constant for a material equal to the stress divided by its corresponding strain. So remember the equation. They should have actually given you the equation also here. So this is the equation. We'll show you the original one. This is the one. Okay, so in words, this is actually that stress divided by its corresponding strain. Then stress is force over cross-sectional area, strain is extension over original length. Here you can see the units cancel out, so this is not having a unit. then stress is newtons per square meter, which is the same as pascals. Okay, so that's the end of that. Make sure you do all these questions and check the answers in the answer sheet. This is to ensure that you have understood everything here. Again, this is very simple. Only thing is you have to remember these three equations, this, and this, and you can get the another one for this actually, which is based on what we have here, which is this. So you may have to use this form also in the questions in your exam papers. Alright, so remember this, and that's the end of that lesson on Young modulus, stress and strain. 4.2 part 3 is about the graphs.